Hello and welcome to discussion 12 for CS61B. Today we're going to talk about sorting. So, first things first, some announcements. Let's get into review. So let's go sort by sort first and kind of discuss the differences between each sort. So the first one we're going to talk about is insertion sort. So insertion sort involves taking each item from the list and inserts it into its correct place by swapping backwards. So basically you'll start with this 3. I think before the 3, so we're going to leave it in place. For the 5, we're going to compare it to the item immediately before it, and it's not less than 3, so we're going to leave it also in place. Now we're going to start with 1. 1 is less than 5, so we're going to swap the 1 and the 5, which is going to make the 1 go back by 1. And then we're going to compare the 1 and the 3. And again, 1 is less than 3, so we're going to swap it, so the beginning of our list would look like 1, 3, 5. And then we do the same thing with 2. And basically the idea here is we are just going to be swapping continuously backwards over and over again until we get to the point where when we get the last element and our list is fully sorted. The runtime of this sort ends up being a big O of n squared, because in the worst case, you'll have to do about n squared swaps. However, it is possible for it to take less than that amount of time. If your list is already very close to being fully sorted, then it'll be closer to a linear amount of time, because for each element, you'll only compare it to the one immediately before. And if your list is nearly sorted, it'll already be in the right place or very near the right place already. Next, we have selection sort, which is easy to confuse with insertion sort, but there's a little bit of difference. So selection sort, you scan the whole list each time. You scan the remainder of the list each time, and you find the smallest element. So first you'll find this 1, and then you swap it with the first unsorted element. So in this case, we'll swap the 1 and the 3. And then once that's done, you'll look at the next 4 items, and you'll scan the list again, trying to find the next smallest element, which would be 2. And then you would swap the 2 and the 5. And you would keep going like that, basically, until you have sorted the entire list. Now, selection sort, unlike insertion sort, takes theta of n squared time, because every single time, no matter where the smallest element is, you are going to have to scan that whole list. So there's no way for you to do it in a way where it takes less than n time at each step. So it's going to be n squared time no matter what. Next, we have merge sort. So in merge sort, you split the list in half, and then you apply merge sort to each half, and then you merge the 2 halves together. Now, when you merge 2 halves together, what you're going to do is you look at the first element of the first half and the second element of the second half. The first element of the first half and the first element of the second half, and you compare which one is smaller, and whichever one is smaller, you're like, okay, that's going to be the first element of our merged version. And then you move the pointer in that half down by 1, and then you compare those 2 elements. So basically, every time you merge, you're going to compare every level of this, you're going to compare n elements, and because you're just dividing in half until you hit 1 element per thing, and then you merge your way up, there are log n levels to this, so the total runtime of this is going to be n log n. Heap sort involves using the heap property that we have discussed in past discussions. So we're going to heapify the array into a max heap and then pop the largest element off of our max heap and then appending it to the end. When we do this, we're going to have to reheapify. So reheapification takes max of log n time. So the total runtime of heap sort is n log n, because we're going to have to reheapify every time we pop something off. Now, quick sort picks a partition and uses Horace partition or some other partitioning scheme to divide the list so that everything greater than our partition is to the right of our item and everything less than the partition is on the left of our item. And then basically, and it's nice because it's kind of similar to merge sort in that you're kind of dividing the list in that way, but that partition, how you pick your partition really impacts the runtime of this sort. So in the worst case, it'll take n squared time if your partition happens to be at the end of your list. Like if you pick 1 as our partition here, there's no elements less than 1. So in effect, we haven't really done much. So in the worst case, it'll take n squared time. However, if your partitioning scheme is very good and you happen to pick partitions that are in the middle of the list every time, in that case, it'll take roughly n time as well. Now we're going to talk about counting sorts. So LSD is least significant digit radix sort. And how this works is that the first step, you look at all of the smallest digits. So here 0, 3, 2, 2, and 9. And you sort this based off of the value of this. So the 120 will come first, then 112, then 342, then 923, then 199. Once that's done, then we're going to sort it by the second largest digit and do the same thing, and etc. until we have sorted it up until the greatest digit, at which point we will have everything in sorted order. The runtime of this is W times n plus R, where n is the number of items in our list, R is the size of our radix. So in this case, since we're dealing with integers, the size of our radix is going to be 10 because each digit can have one of 10 values, and W, which is the length of our largest term or word or number. So in this case, W is equal to 3. So since W and R in this case are relatively negligible, even as n gets really, really big, this is almost actually linear time, which is amazing for a sort. MSD Radix Sort is very similar. The only difference is that you start from the largest digit and you go to the smallest digit. Now, when you do this, there are some extra steps you have to take in order to prevent things from getting messed up. And the big thing is that you can't cross over once you have put two items in the same bucket, and the way you choose your buckets is obviously by the digits themselves. So let's say we start with the most significant digit. We have 120, 112, and 199. Those are in one bucket because their most significant digit is a 1. And then we have 342 in its own bucket and 923 in its own bucket. Now, when we sort by our second most significant digit, we're not going to be allowed to cross over between buckets because that'll mess us up, right? Because we know that 342 and 923 are definitely bigger than anything in the bucket that starts with a 1. Now, within that one bucket, then we're going to sort by our second most significant digit. And then again, once we've done that, 112 and 120, because their second digits are different, you can't cross them over. And that's because no matter what third digit you get for 120, it's never going to be less than whatever comes after this 1 and 112. This one has a runtime of big O of W n plus R, and that's because of the early stopping that is allowed due to the bucket sort of rule that we have going on here. So it's a little faster than LSD sort, but it is more complicated to implement. So first things first, let's do some quick sort, some mechanical practice. I'll give you a chance to try it out, and then we will go over it together. Okay, let's give it a shot. So here are the complete steps for quick sort. Let me turn on my laser pointer. So first of all, what we're going to do is pick our first pivot. So we're picking our first item. 106 is what we're going to get. And if we look at this list, everything is larger than 106. Not a great pivot. So 106 is going to go down straight here. This part of our list is already sorted. 106 is already in the correct place. So we're never going to have to look at this again. The rest of the list, however, still needs some maneuvering. So we have this at this point with 351 as our next pivot, and that's going to go right here with 214, 172, and 333 being less than it, and 873, 615, and 564 being greater than it. So what's going to happen is 351 is in the right place, 106 is in the right place. We're not going to look at those anymore. We're looking at 214 as our next pivot for this segment and 873 for our new pivot for this segment. And again, 214 is in the middle, so we're going to end up with 172 and 333, which are both going to be pivots now as well, but they're pivots for no reason because there's nothing else in their segment. So we're just going to leave them as is. 873 is larger than the other two numbers, so it goes right here in its rightful place. And 615 is our last real pivot, and we are just going to sort this small segment here, and it gives us this final list sorted from smallest to greatest correctly. next, let's do the same thing but with merge sort, and I'll give you a second to try it out. Okay, let's go over it. So, for merge sort, we start it's kind of like the opposite of quick sort in that we start with everything in its own little boxes and then we merge the groups together. So 106 and 351 merge to form this segment. 214 and 873 merge to form this segment. 615 and 172 merge to form this segment, and 333 and 564 merge to form this segment. Now these two segments are going to merge together, so 106 is smaller than 214, so that's going to go here first. But 214 is smaller than 351, so that's going to be the second element. 351 is smaller than 873, so 351 goes as the third element, and then all that's left is to put 873 in its place at the end. Next, we're going to do these two together. So 172 is smaller than 333, so 172 goes here first, but 333 is smaller than 615, so that goes here. 564 is also smaller than 615, so that goes next. And all that's left is put 615 at the end. Now we're going to merge these two larger sections together. So comparing 106 and 172, 106 is smaller. Comparing 214 and 172, 172 is smaller. Comparing 214 and 333, 214 is smaller. Comparing 351 and 333, 333 is smaller. Comparing 351 and 564, 351 is smaller. Comparing 564 and 873, 564 is smaller. Comparing 615 and 873 and 615 is smaller, which just leaves 873 at the end. Okay, last one for mechanical practice. Let's do MSD Radix Sort. Okay, let's go over it. So, first things first, we're going to sort by this last digit. So 351 has a 1 as its least significant digit, so that goes first. Then 172 because it has a 2. And then 873 and 333 both have 3 as their last digit, so they go here. Then 214 and 564 both have 4. And then 651 has 5 and 106 has 6. So this is an order by least significant digit. And now we're going to sort by the second least significant digit. So first, the only thing we have that's 0 is 106. And we have two different numbers that both have 1 as their second least significant digit. So we're going to go in order from left to right. So 214 goes first and 615 goes second because that's the order they were in the previous iteration of LSD. Next, we have 333, which is the only thing that has a 3 there, and 351 and 564, which are the only things that have a 5 and a 6 in that spot. And lastly, we do the same thing that we did for the the same thing we did for the 1 in the second place, as we're going to do the same thing we did earlier here between 172 and 873. Going from left to right, 172 appears earlier, so that's going to appear earlier in this list as well. Lastly, we are going to do the same thing but by the most significant digit. So 106 comes before 172 in this iteration of the list, so it's going to stay that way down here. 214 is by itself. 333 comes before 351 in the previous iteration of the list, so it's going to stay that way. And the others are the only one of their number that appears, so it's kind of how it's supposed to be. Okay, now let's get on to something more interesting. So we're going to do some identification problems. So the goal here is to identify what sorting algorithm these steps display. And these are going to be some intermediate steps. So they're not going to necessarily be like the beginning and the end. There'll be some steps that are somewhere in the middle. I'll give you a chance to try it out. Okay, let's go over it. So for this first problem, this is a quick sort. So the way you can tell when a problem is quick sort is that you'll notice a number move to a place and just stay there. It'll be stuck there. Now, it won't necessarily be any particular number, but it'll get stuck there like this 12 does, because the pivot always ends up in the right spot within the final answer when it's the pivot. Additionally, you'll notice that everything to the left of that number is going to be smaller than it, and everything to the right of that number is going to be greater than it. Okay, let's do another one. What about this one? Okay, so this one is going to be insertion sort, and the way you can tell if something is insertion sort is because the first half of the list will be perfectly sorted, or the first however much of the list will be perfectly sorted, but the second will be untouched. This is important because if it is selection sort, you'll still see that same first part of this list being perfectly sorted. However, the second half of the list will most likely be messed up in some way, because what are the chances of all of the smallest elements being already at the beginning of the list? So if it was selection sort, maybe the 4 would have started off here, and at some, or like for instance, if it was selection sort, this 20 would have already been moved up here at some point. Okay, another one. Let's give it a try. Okay, let's go into it. So this one is going to be MSD Radix Sort. You can tell when something is a radix sort because naturally all of the numbers will be grouped by either their most significant or least significant digits place. So in this case, you notice that all the ones are together, but they aren't in order internally. So like, it's not like it's sorted already. It's like all the ones places just happen to be together, but they're unsorted. 2's places and then 3's places. And that's a key indicator that it is MSD. For LSD, it'd be the same thing, but the opposite, where the last digit would be all in order already. Okay, let's do another one. Okay, let's see. So this one is going to be merge sort. Now you can tell it's merge sort because you notice that there are some switches happening, but they're all very local. So for instance, right here, we see that these 2 elements have swapped places. These are in the same spot. These 2 have swapped places, and these 2 have swapped places. And then in the next iteration, you see that, again, this 4 have sorted themselves, and these 4 have sorted themselves, but we haven't seen any crossing, which we would see with most of the other sorts, such as heap sort or quick sort or any other sort. So that's a key indicator of merge sort, is when like the swaps that are occurring are all very local, but they're happening on both sides. So it isn't like insertion sort where it's only happening at the beginning of the list. Okay, I think this is our last one. Okay, so the answer here is going to be heap sort. So the key indication for a heap sort is the heapification. As you can see here, this is actually a heap right here. Another key indicator for heap sort, especially later on in the process, is that it will the numbers at the end will be sorted, but not at the beginning. So for instance, if this were to keep going, this process, the 54, and then there'd be 44, and etc. And so the beginning of our heap sort, or our set, would be unsorted because it is forming a heap, so it literally cannot be sorted. But the end will be sorted because that is the sorted half of our list, which is unusual because most of our sorts sort from left to right, not from right to left. Okay, now that we've done some identification, let's just do some conceptual problems. So here's parts A through E of number 3. I'll give you a chance to think it over, and then we'll go over the answers to each of these together. Okay, let's go over it together. So this first question is, quicksort has a worst case runtime of n log n, where n is the number of elements in the list we are sorting, and this is false because of what we talked about earlier. If your pivot happens to fall at the very end or the very beginning of the list every single time, in that case, you're actually going to end up with something that resembles selection sort or insertion sort and ends up having an n squared runtime rather than what we would prefer, which is an n log n runtime. Part B asks, if we have a system running insertion sort and we find that it is completing faster than expected, what can we conclude about the input. So there's two options. The first, that the input is very small. In reality, it is actually faster to use insertion sort than any other sort if your input is less than 16 items. There's probably a mathematical proof out there about this, but I know that this is just a fact. Python uses something called Tim sort, and Tim sort, if the number of items is less than 16, it automatically uses insertion sort, and if it's greater than 16, it uses merge sort for this reason. The other option is that the array is nearly sorted already because of what we talked about, where if it's already sorted, then we're not going to have to move elements as far, so we'll have to do fewer comparisons in general. Part C asks, if we give a 5-integer, please give a 5-integer array that elicits the worst case runtime for insertion sort. So as we talked about, if a list is almost sorted perfectly already, the insertion sort is very fast. But if an array is the opposite, if it's the opposite of sorted, as in this case, every single element is going to have to travel the maximum distance, which is going to take the longest amount of time. Part D, true or false, heap sort is stable. This is false. Stability in this situation basically means that if you sort it by one criteria first and then by the second criteria, and two items are equal with regards to that second criteria, they will be sorted by that first criteria within that grouping. And heap sort, this isn't the case because that heapification process kind of mixes everything around. Part E asks, why would someone choose merge sort over quick sort? And the answer is because the worst case runtime of merge sort is always going to be n log n. The best case is also n log n, the worst case is n log n. While quick sort, the worst case is actually theta of n squared. And additionally, merge sort has that stability while quick sort does not. The benefits of quick sort, by the way, is that it is an in-place sort so that you can do it without having to create more arrays. Okay, last bit. So part, I think, F of conceptual sorts. Which sorts do each of the following statements describe? And I believe there are letters associated with each of the sorts in the worksheet. I'll give you a chance to think about it. Okay, let's talk about this. So the which ones are sorted by, bounded by omega of n log n. So omega of n log n means that it can never be faster than n log n. In this case, the answers are quick sort, merge sort, and selection sort. Technically, selection sort is actually lower bounded by n squared, but because this omega isn't necessarily a tight bound, it still qualifies. Merge sort and quick sort both have to take a minimum of n log n. Insertion sort can be faster if the elements are already almost sorted, and heap sort can be faster if the elements are all the same, in which case reheapification does not take the full log n time every single time. What has a worst case runtime that is asymptotically better than quick sorts? And the answer here is B and E, which is merge sort and heap sort, because both of these have a worst case runtime that is n log n, while quick sorts is n squared. In the worst case, what performs theta n of pairwise swaps, and that is going to be C, which is selection sort, because you're only doing one swap per item. You're only swapping once you have found that minimum item. So you will always do exactly n swaps. What takes a long time in selection sort is finding that minimum item. What never compares the same two elements twice? And the answers are quick sort, merge sort, and insertion sort. So quick sort, you are only comparing things with a pivot, and then once you've chosen something, or once you've used something as a pivot, you're not going to touch it again, so you're never going to compare anything else to it. Merge sort, you're only comparing it as you zip it up, and once two things are zipped up, they're in the same group, and so you are never going to have to combine them ever again. And then D, insertion sort, because in insertion sort, you are moving things up that list, so you're never going to need to compare the same elements twice. And then, because you're only comparing things to the things that are immediately to the left of them, and so you'll never have compared it to anything to the right until that element to the right is ready to move up itself. And what runs in best case theta log n for certain inputs? And the answer is none of the above. Everything takes at least linear time because you have to look for every element. You have to look at every element, even if looking at it only takes constant time. That is still linear time, which just takes longer than log n time. Okay. Thank you for listening. This is the end of the worksheet, and good luck. Have a great week. Bye.